This is a continuation of the previous lecture. In the previous lecture, we already explained the duality theorem. Now we'll discuss how we can apply duality theorem to solve the continuous time Fourier transform question. So we'll discuss the first question. Here we need to find the continuous time Fourier transform of the following signal. The signal is given by 1 by a+jt. And we know that this is a signal, and if you substitute this particular question in this particular equation, we will get a complex integration. It's very difficult to solve such kind of integration. So instead of that, we will apply duality theorem here. So if you look at this particular format, 1 by a+jt is almost similar to 1 by a+j omega. So this is actually the transform of e raised to minus at into u of t. It's a non-signal. We already discussed the Fourier transform an exponential signal, and this is standard result. E raised to minus at into u of t, and signal in time domain, and frequency domain representation or continuous time Fourier transform of the signal is 1 by a+j omega. If we compare these two signals, you can see that this is almost similar to 1 by a+j omega. Instead of omega, it is t. So we can apply duality theorem here. A similar signal exists in the time domain. So according to duality theorem, here you can see that assume that the signal x of t is e raised to minus at into u of t. Okay, it's continuous time Fourier transform x of omega instead of x of j omega. I'm using x of omega in duality problem for the simplicity. Divided by, the answer is 1 plus j omega. Okay, or I can write x of j omega also. Now if you compare these two equations, there is another signal which is 1 by a+jt. So we need to find the Fourier transform of this signal, and this is x of omega. So we can write capital X of t 1 by a+j into t. And the continuous time Fourier transform of this particular signal, according to duality theorem, it's 2 pi into x of minus omega. Means 2 pi into x of t. Small x of t is e raised to minus at into u of t. So e raised to minus at into u of t. You need to substitute t is equal to minus omega in this particular equation. So if you substitute this, you will get 2 pi e raised to minus a, and t is minus omega, so you will get e raised to a omega, and in place of u of t, you will get u of omega. So the final answer, or the Fourier transform of the signal 1 by a+j into t can be written as 2 pi e raised to a omega into u of omega. Okay. So this is the final result for this particular question. And one more thing, here it is actually u of minus omega, and this is step signal. And if you find the u of minus omega and u of omega is a signal which is exists in the frequency domain, and this is actually u of minus omega, because we will substitute t is equal to minus omega in this particular equation. So here it is. So this is the step signal which exists in the frequency domain. And now we'll discuss. So instead of using the direct method, we are using duality property to solve this particular problem. Now we'll discuss another question. And here the signal is given by e raised to minus 2 omega and u of omega. That is, we need to find the inverse continuous time Fourier transform of the signal. X of omega is equal to e raised to minus 2 omega into u of omega. So if you look at the previous question, it's almost similar. Here we need to find the inverse Fourier transform. Again, to find the inverse Fourier transform, there is an equation that is 1 by 2 pi. This is x of t can be calculated by using the formula integral minus infinity to infinity x of omega into e raised to j omega t d omega. So instead of using this particular equation, again I can use duality properties here. See, if you look at this particular question, here assume that this is x of t e raised to minus 18 into u of t, and this is x of omega. Okay. Now here the question is given like e raised to minus 2 omega into u of omega. So this is almost similar to e raised to minus 80 into u of t. So again, you can see a similar shape, but it is in the time domain. The question is given in a frequency domain, but a similar result we know in time domain. So by using this result, I can apply duality theorem. Now we can write x of t here. If you write x of t, capital X of t, by applying duality theorem, that is 1 by a plus j into t. We know the Fourier transform of this particular signal is 2 pi into x of minus omega. And here 2 pi into x of minus omega means we need to substitute, this is actually x of t in this particular question. So that is e raised to minus 80 into u of t. In this particular equation, we need to substitute t is equal to minus omega. And now if you substitute t is equal to minus omega, it becomes e raised to a omega into u of minus omega. So now we got almost similar to the previous question, but we need slight modification. So that is a Fourier transform of, so one more point, this is actually 1 by a plus jt, and it's 2 pi into e raised to a omega into u of minus omega. And assume that if a is equal to 2, we can write it simply 1 by 2 plus j into t. It becomes 2 pi into e raised to a omega into u of minus omega. Okay. So assume that the constant a is equal to this particular question. And we need the inverse Fourier transform of e raised to minus 2 omega into u of omega. But actually in this particular question we got, here also we need to change a is equal to 2, e raised to 2 omega into u of minus omega. So if you change omega to minus omega, you will get exactly the same question. So now we can apply the time reversal property. Actually, by applying time reversal property, we know that x of t or x of minus t becomes x of minus omega, or x of minus omega, or x of minus j omega. So by applying time reversal property in the previous problem, we will change t to minus t. So it becomes 1 by 2 minus j into t. And the Fourier transform of the signal is simply x of minus omega. That is 2 pi e raised to minus a omega into u of omega. So from this particular result, we can conclude that the inverse continuous time Fourier transform of the signal e raised to minus a omega into u of omega can be written as, this is the inverse Fourier transform of e raised to minus a omega into u of omega can be written as 1 by 2 pi into 1 by 2 minus j into t. Okay. Now so the previous question and this one is almost similar, the same result we are using, but one question is to find the inverse continuous time Fourier transform, and the previous one is to calculate the continuous time Fourier transform. One is a forward transform, and here it is a inverse transform. Now we'll discuss another question. Here we need to find the continuous time Fourier transform of the signal 1 by a square plus t square. Again, here we will apply duality theorem to solve this particular problem. We will also compare with the standard equation, that is e raised to minus a modulus of t. And the Fourier transform of the signal, assume that this is x of t, e raised to minus a modulus of t, and the continuous time Fourier transform is 2a by a square plus omega square. And assume that this is x of omega. And if this is x of omega, you can write x of t, capital X of t, can be written as 2a by a square plus t square. Okay, instead of omega, you can write t. That is x of t, capital X of t. And the continuous time Fourier transform of the signal can be written as 2 pi into x of minus omega. And here 2 pi x of small x of t is e raised to minus a modulus of t. So you can write e raised to minus a modulus of t at t is equal to minus omega. And if you substitute that, you will get e raised to minus a and minus omega. And this is a modulus, so we can simply write 2 pi e raised to minus a modulus of omega. Now we got the result, and in this particular question, it's 1 by a square plus t square. So if you want to find the Fourier transform of 1 by a square plus t square, there is actually a constant 2a in this particular question. So if you apply the linearity property here, we can multiply with a constant. So we divide with 2a in both sides. It becomes 1 by 2a into 2 pi e raised to minus a modulus of omega. And 2 will be cancelled and becomes, the final result becomes, or the Fourier transform, continuous time Fourier transform of the signal 1 by a square plus t square is equal to pi by a e raised to minus a modulus of omega. Okay. Again, by using the standard result, I can very easily calculate the Fourier transform. So now we'll discuss again similar to the previous question, but here we need to find the inverse Fourier transform, and the signal is e raised to minus modulus of omega. And if you look at this particular question, again it's similar to e raised to minus a modulus of t. Instead of t, it's omega. So again, you can apply duality theorem, because the signal shape is almost similar. Only difference is that this is given in time domain and here it is given in frequency domain. So we need some kind of rearrangement by using duality. So this is capital X of omega. So we can write capital X of t is equal to 2a by a square plus t square. And the continuous time Fourier transform of this particular signal is by applying duality theory, it's 2 pi into x of minus omega. Or you can write 2 pi into x of t is e raised to minus a modulus of t. So e raised to minus a modulus of minus omega. We need to substitute t is equal to minus omega. And here it is modulus. So e raised to minus a modulus of omega. Now we need to rearrange this. That is 2a by a square plus t square, and the continuous time Fourier transform is 2 pi into e raised to minus a modulus of omega. Now in this particular question, it is given e raised to minus modulus of omega. So we can rearrange this. So that is a is equal to 1. A is equal to 1, and 2 will be cancelled. So finally it becomes 1 by pi 1 by a square plus t square is equal to e raised to minus modulus of omega. So the inverse continuous time Fourier transform of the signal e raised to minus modulus of omega is equal to 1 by pi into 1 by a square plus t square. Okay. Now we'll discuss another question. Now we'll discuss another question. Here we need to find the continuous time Fourier transform of the signal j by pi t. Okay. Again, this is again a standard signal, and if you look at this standard equation of or the transform of signum function. Okay. Signum signal means it's a signal whose magnitude is 1 for t greater than 0 and -1 for t less than 0. So this is a signal signum of t. Okay. And the transform of the signal is 2 by j omega. And if you know the result, you can compare it with the equation. It's also similar to something j by pi t. Anyway, omega in the denominator. Here also that t is in the denominator. Again, we can compare these two questions, and we can apply the duality theorem. So the shape is almost similar to the question. Now, assume that the signal x of t is signum of t, and 2 by j omega is Fourier transform x of omega. Now we can write x of small x of t, capital X of t. The function will be like this: 2 by j into t. Okay. And the continuous time Fourier transform of this particular signal, you can write by using duality property, that is 2 pi into x of minus omega. And here it is small x of minus omega, that is x of small x of t is signum of t. So we can write signum of minus omega. Okay. And signum of minus omega is an odd function. So signum is an odd function, and signum of omega means again a signal in the frequency domain. The shape is almost similar to the time domain signal, 1 and -1 here. And if it is signum of minus omega means it's a time reverse signal. It will be like this: 1, and here it is -1. So this is signum of minus omega, and this is an odd signal. So you can write a signum of minus omega is equal to minus signum of omega. So you can replace this 2 pi into minus. I can write minus 2 pi signum of omega, and you can see that this is a Fourier transform of the signal 2 by j_t, and this 2 will be cancelled. And now if you look at this particular question, there is a j in the numerator, so you can multiply with the j by applying the linearity property. So if you multiply j, it becomes j. Sorry, you need to multiply. Here we need to make it j. So I need some rearrangement in this particular question. For that, so anyway, also pi is required at the equation. So I can write signum omega at the right side, and remaining quantities I can write here. So there is one minus. So minus, and here it is j, and here it is pi. And only difference is that the j is a numerator. So if you multiply j, the numerator and denominator, you will get j square at the denominator and j at the numerator, and minus will cancel. So multiply j, the numerator and denominator in this particular equation. So it becomes j by pi t, and the transform of the signal will be signum of omega. And the continuous time Fourier transform of the signal j by pi t is signum of omega. And this is also a very interesting question. Now you can apply another question. Here, determine the continuous time Fourier transform of the signal 1 by t. Here also you can apply duality theorem, because it's a slightly modified version of the previous question. Here we can see the 2 pi j omega, that is t in the denominator here omega. So you can apply duality theorem here. This is x of t and this is x of omega. So from this we can write capital X of t is equal to 2 by j omega, which is 2 by j omega. It's 2 by jt, and the continuous time Fourier transform this particular signal is 2 pi x of minus omega. By using duality property you can write, so it becomes 2 pi and x of t is signum of t. You can write it's signum of minus omega, and this is an odd function. We already explained that, so we can write 2 pi into minus 2 pi into signum of omega. You can write, and this is the Fourier transform of the signal 2 by j into t. And from this apply linearity property. You can write you can with the scalar multipliers. Now 2 will be cancelled and j will go to the right side. So you can write 1 by t is equal to minus j pi, it's signum of omega. And the transform of the signal, continuous time Fourier transform of the signal 1 by t is equal to minus j pi signum of omega.